Now we are going to solve a problem on unsymmetrical fault analysis, the single line to ground fault. Two synchronous machines are connected through three-phase transformers to the transmission line as shown in figure. Two machines are connected to a transmission line through three-phase transformers. The rating and reactances of the machines and transformers are machines 1 and 2, 100 MVA, 20 kV, XD double dash is equal to X1 equal to X2 equal to 20%, X0 equal to 4%, and Xn is equal to 5%. Transformers T1 and T2, 100 MVA, 20 bar 345 kV, X is equal to 8%. Both transformers are solidly grounded on two sides on a chosen base of 100 MVA 345 kV in the transmission line circuit. The line reactances are X1 equal to X2 equal to 15% and X0 equal to 50%. The system is operating at nominal voltage without pre-fault current when a bolted line to ground fault occurs on phase A at bus number 3. Determine the subtransient current to ground at the fault. So we have a power system network like this, and a single line to ground fault is occurring on the transmission line at this particular point, and we have to calculate the subtransient current to ground at the fault, which is nothing but the fault current flowing towards the ground from the fault point, through the fault point. So we have to calculate the fault current in this particular case. So this is a single line to ground fault, and we know in this particular case the fault current IF will be equal to 3 times EA divided by Z1 plus Z2 plus Z0 plus 3ZF. So here it is given that the fault is bolted. A bolted single line to ground fault occurs on phase A. Bolted fault means a direct short circuit on phase A, or fault impedance ZF is 0. So in this case the fault is bolted fault. Therefore ZF will be equal to 0, and the fault current IF will be equal to 3 times EA divided by Z1 plus Z2 plus Z0. So this is the value of fault current. So here we are considering a complete power system network. So if a fault occurs on this particular point, current from the remaining parts of the system will flow towards this fault point. So Z1, while calculating the fault current, Z1 will be the total positive sequence reactance of this entire system. Similarly, Z2 and Z0 represents the total negative and zero sequence reactances of this entire system. Okay. So if we have to calculate the total positive sequence, negative sequence and zero sequence reactances, we have to draw the corresponding sequence networks. We have to draw the positive sequence network, negative sequence network and zero sequence network for this complete power system network. Okay. Now we know that the positive sequence network is same as the reactance diagram. Positive sequence network and reactance diagram are the same. Okay. Now see, for drawing the reactance diagram, we need the per unit impedance of all the components with respect to a common base. So here per unit impedances of each of the components are given, and they are based on a common base. So here these two machines are having identical ratings. Similarly, these two transformers are having identical ratings. Okay. Now for this transmission line also, the MVA is 100, which is same as that of these machines and the transformer. 100 MVA and voltage is 345 kV. For the transmission line, base is 100 MVA, 345 kV. So which is the kV base corresponding to this transmission line? Okay, 345. The secondary voltage of this transformer is 345 and the voltage of this winding is also 345. So the voltage kV base for this line is 345 and a base MVA of 100 is used. So for all the components, the impedances are already specified on a common base. So we don't have to convert the per unit impedances into a common base. They are already expressed with respect to a common base. See, machine 1 100 MVA 20 kV, machine 2 is also 100 MVA 20 kV. Now the transformer is also 100 MVA. Both transformers are 100 MVA. Primary voltage is 20 and here also it is 20. This winding is having 20 kV. And we have discussed the case of transmission line already. So we don't have to convert the impedances. We can directly use the impedances that are given. They are already expressed on a common base. So we have to calculate total positive sequence reactance, total negative sequence reactance and total zero sequence reactance. So for that, let us draw the positive sequence network, negative sequence network and zero sequence network. So first of all, let us draw the positive sequence network. So let us draw the positive sequence network. So we know the positive sequence network of a generator will have the positive sequence impedance in series with a voltage source. Okay. Now that of the transformer, the positive sequence network of the transformer will have a series impedance only, series reactance, which is the positive sequence reactance of the transformer. Then the transmission line is also represented as a series reactance in its sequence network. Then transformer T2, the second transformer, and finally the machine 2. Machine 2 is also, it is a synchronous machine. So the positive sequence reactance in series with a voltage source. Okay, so this is the positive sequence network. Now let this be E1 and let this be E2. Okay. Now this is positive, we are drawing the positive sequence network. So here we have to represent the positive sequence reactance of the generator, which is 20% or J 0.2 per unit. So next is a transformer. For the transformer, the reactance is given as 8%. That means all the sequence reactances x0, x1 and x2 are 8%. So it is J 0.08 per unit. Then for the transmission line, x1 equal to 15%, J 0.15 per unit. Transformer T2 is also having the same rating, so J 0.08. Then motor, machine 2 is having same rating as that of machine 1, so J 0.2 per unit. And see, the fault is near to bus number 3, that is on the transmission line. Okay, so it will be here on the transmission line near to transformer T2, near to bus number 3. Fault, it is given that LG fault occurs on phase A at bus 3, that is near to transformer T2, second transformer. So we can represent the fault here. So this is the fault point. Now we need Z1, that is the total positive sequence reactance as seen from the fault point. So we cannot calculate Z1 as the sum of all these reactances, but it should be the equivalent positive sequence reactance as seen from the fault point. So if we look from this fault point, these two reactances are in series and these three are in series. And this series combination is in parallel with this series combination. So we can write Z1 as these three are in series, that is J 0.2 plus J 0.08 plus J 0.15. It will be 0.35 plus 0.08, that is 0.43, J 0.43. So and this is parallel to, that is J 0.43 parallel to J 0.28. So this will be equal to J 0.43 into J 0.28 divided by J 0.43 plus J 0.28, and the answer will be J 0.1695 per unit. So this is the total total positive sequence reactance of this particular diagram, this particular power system network when a single line to ground fault occurs on bus number 3. Now we have to calculate the total negative sequence reactance Z2. For that we have to draw the negative sequence network for the complete power system network. So in the negative sequence network, the machine 1 will have the negative sequence reactance only. There is no voltage source. Transformer T1 has a series reactance, transmission line has a series reactance, and transformer T2 has a series reactance, and machine 2 will also have a series reactance only. So the values are J 0.2 for the machine 1 negative sequence. This is the negative sequence network. Negative sequence network. So J 0.2 per unit is the negative sequence reactance of the machine 1. Then for transformer it was J 0.08. For transmission line J 0.15. For transformer T2 also J 0.08. For machine 2 it is J 0.2. So fault was at this point near to bus number 3, that is near to transformer T2 on the transmission line. Now Z2, the total Z2, total negative sequence reactance of this system will be the equivalent negative sequence reactance with respect to the fault point. So same, we will get the same value as in the case of the positive sequence reactance. These three are in series, these two are in series. Then this series combination is in parallel with this series combination, and we will get Z2 as J0.1695 per unit, which we have already calculated in the positive sequence network. Now moving on to the zero sequence network. Okay. So zero sequence network is different from the positive sequence and negative sequence network, and we have to take greater care while drawing the zero sequence network. There are some points to be considered. So first is the generator. Let us draw the zero sequence network, and first component is the generator. So in the generator, while we are drawing the zero sequence network of a generator, it will have the zero sequence reactance only and no voltage source will be there. So let us draw the zero sequence reactance of the generator. And what is the value of the zero sequence reactance? The total zero sequence reactance will be equal to zero sequence reactance per phase of the machine plus 3 times the neutral grounding reactance. We know that the total zero sequence reactance is equal to zero sequence reactance per phase plus 3 times the neutral grounding reactance. So it will be, for the generator, X0, the zero sequence impedance per phase is given as 4% and the neutral grounding reactance is 5%. So this will become J 0.04 plus 3 into J 0.05, which is equal to, what is the value? So let me draw the diagram at some other place. So x0 is equal to xg0 plus 3xn, which is equal to J 0.04 plus 3 into J 0.05, that will be equal to J 0.15 plus J 0.4. Okay, J 0.04 plus J 0.15. So this is the total zero sequence reactance, or J 0.19. We can represent it as J 0.19. So let us draw the zero sequence network. So for the machine 1, total zero sequence reactance is J 0.19, J 0.19 per unit. Okay. Now coming to transformer T1. So for the generator, total zero sequence reactance equal to zero sequence reactance of the generator plus 3 times the neutral grounding reactance. So it will be J 0.19 per unit. Then moving on to the second component, that is transformer T1. Now, while drawing the zero sequence network of a transformer, we have to check whether the winding is star connected or delta connected, and draw the zero sequence network accordingly. So see transformer T1, primary is delta and secondary is star connected and star point is grounded. So if a winding is delta connected, zero sequence current can circulate in that winding but cannot flow through the line connected to it. So zero sequence current of this transformer will not flow through this line, and here the secondary is star connected and star point is grounded, so there is a path for zero sequence current to flow. So in this particular transformer, there is a path for zero sequence current to flow, but delta connected winding will not be connected to the line, the corresponding line. Zero sequence current, if the winding is delta connected, zero sequence current cannot flow through the line connected to that particular winding. So how will you draw the diagram? Here we have, after machine 1, we have bus number 1. So it will be, so let this be the bus number 1, and as the primary winding is delta connected, we cannot connect the winding to the line, corresponding line. So here there will be an open circuit, and this is the transformer reactance, that is J 0.08 per unit, zero sequence reactance of the transformer, and the primary is delta connected, so the winding cannot be connected to the line, corresponding line. So here there will be an open circuit, and the secondary is star connected and star point is grounded. So here there will be a continuous connection to the second component, that is the transmission line. So this side of the winding will be connected to the corresponding transmission line. But the zero sequence current has to flow, circulate through this winding. So there should be a path for the zero sequence current to circulate in the winding. If there is an open circuit here, current from this path cannot flow towards this, through this winding. If we keep this section open circuited, zero sequence current cannot flow through this transformer winding. But there should be a path for transformer current, for zero sequence current to circulate in the delta connected winding. So we have to provide that path here. Okay, so this is the zero sequence network of a delta star grounded transformer. Now this is the transmission line, and a line is having a reactance J 0.15 per unit, and again a transformer. So check for the winding connection. So it is a star delta transformer, ungrounded star delta. So one of the winding is ungrounded star, means there is no path for the zero sequence current. So zero sequence network will be an open circuit. Okay. So if this is the transformer reactance, zero sequence reactance, then we have to represent an open circuit here. Okay. And finally machine 2. So it represent zero sequence reactance of machine 2, and this is also x0 plus 3xn, that is J0.19 per unit. Okay. So for transformer T2 also this is J0.08 per unit. Now fault is on this particular point. Okay. This is the fault, and now see the total zero sequence reactance from as seen from this fault point. So while calculating the total zero sequence reactance or equivalent zero sequence reactance of this particular network, consider those reactances only through which the fault current can flow. See, here as there is an open circuit here, current from this generator cannot flow through the fault point. So, but a current can flow through this path and through to the fault point. And similarly, there is an open circuit here, so current cannot flow from this machine to the fault path. So the fault path will consist of only these two reactances. Fault current, zero sequence current will flow towards the fault point through these two reactances only. There is a path for the current flow. Starting from here, current will flow through these two reactances and to the fault point. So as there is an open circuit here, no current can come from this reactance. So only these two reactances are there in the equivalent zero sequence network. And Z0 can be written as J0.15 plus J0.08. So this is note J0.15 for the transmission line. See, for the transmission line, zero sequence reactance is 50%. So that is J0.5. So this is J0.5 per unit. So J0.5 plus J0.08, which is equal to J0.58 per unit. Okay. So we got Z0, Z1 and Z2. Then we can calculate the fault current. Fault current IF will be equal to 3 times EA divided by Z0 plus Z1 plus Z2, which is equal to 3 into 1 angle 0 divided by J0.58 plus J0.1695 plus J0.1695, which is equal to minus J3.264 per unit, which can be written as 3.264 angle minus 90 degree. So this is the per unit value of the fault current. Now we have to calculate the actual value. So for calculating the actual value, we need the base current. Base current IB is equal to MVA base into 10 raised to 3 divided by root 3 into kV base, which is equal to MVA base was 100 into 10 raised to 3 divided by root 3 into kV base. So while taking the kV base, we have to take the base kV at the fault point. So fault was on the transmission line, and there the base kV was 345. So we'll get on solving this, we'll get the value of base current as 167.348 ampere. 167.348 ampere. Okay, now actual value of fault current is equal to per unit value into base value. That is, let us take the magnitude of the per unit value 3.264 into the base current 167.348, which is equal to 546.22 ampere. 546.22 ampere. So this is how we can calculate the fault current in this particular case. And now this question can be asked in many ways by changing the transformer winding configuration. So each time we have to draw the zero sequence network of the corresponding configuration. And while taking the total zero sequence reactance, consider only those resistances, those reactances through which the current can flow towards the fault point.